All right, let's do some homework problems. So we're going to start with number 124 from the book, which says, assume f and g are both differentiable. They're differentiable for everything in their domain. For all x, actually. Find the derivative of the function h, where h is fg over 2. We're looking at 124. H of x is f of x times g of x over 2. And we want to know what h prime of x is. So let's do this in stages. H prime is the derivative of h. Now be very careful, because you might see divide by 2, I have to use the quotient rule. And the quotient rule will work here, but there's an easier rule as well. Notice that this inside, that's just the same as 1/2 times f of x times g of x. We can use a constant multiple rule instead and just factor out the 1/2. So it's 1/2 times the derivative of f times g. And now we can use the product rule instead. And product rule is a lot easier than quotient rule. So product rule tells us derivative of the first times the second plus the first times the derivative of the second. And you could either have this as your final answer or distribute that 1/2. Either one would be okay. Usually this is going to be the more common thing to see. And that's all there is to it. All right, that is the derivative of h. Let's do 128 next. Similar idea, if I remember right. Assume f and g are both differentiable functions and they have the following values. Find h prime of 3 if h of x is 2x plus f times g. So h of x, 2x plus f times g. This is going to follow a similar line of logic. We first have to find, we first have to find out what h prime is. Well, let's use what we know about derivatives. That's going to be the derivative of the first function plus the derivative of this. And again, we'll use the product rule. F prime of x, g of x plus f of x, g prime of x. Now, specifically, we want to know what is this derivative at 3. So just plug in 3. It's going to be f prime of 3, g of 3, plus f of 3, g prime of 3. What is f prime of 3? Careful when you read the table. That's when x equals 3. When x equals 3 is this column. We want to know the derivative of f here. It's going to be 8. Times g, the function value, also at 3. That's -4. Plus f of 3, the function value f at 3 is -2. Times g prime of 3, the derivative at 3 of g is 2. And then just simplify. That's 2 minus 32 minus 4. That is -34, I believe. That's how you do it. Let's see it. Let's do some wackier problems. 141. Find the equation of the line passing through the point 3, 3 and tangent to the graph. Now, this is not as exciting as I thought it was going to be. All right, whatever. Sorry, it's not as hard. I'm sure you're very disappointed. So we need to find the tangent line, where f of x equals 6 over x minus 1. And we're looking tangent line at this point. Now you might want to be able to use the power rule and say, oh, we can write this as 6 times x minus 1 to the -1st power. But the problem with writing it that way is that we can only use the power rule for x's, we have an x minus 1. That's going to require something called the chain rule. So we actually do have to use the quotient rule here. All right. So f prime of x is low d high, low times the derivative of the high function is 0, minus high d low, what's the derivative of the bottom function? It's a slope of x minus 1, which is just 1. Square the bottom and away we go. It's good to go off to the side and calculate these derivatives, but we usually use f and g. I didn't do it this time, but if you use the quotient rule, which you should be able to do, and have this be your top function, and this be your bottom function, should be able to get this. And now we just simplify. That's just negative 6 over x minus 1 squared. So it turns out, actually, that this function behaves very similarly to how you would think it behaves from the power rule. Chain rule. We'll talk about that later in chapter 3. That is actually what we can use here, so we don't have to use the power rule. But we want the equation of a tangent line. So what's the slope of the tangent line? At our point, that's an x-coordinate of 3. So that's going to be negative 6 over 3 minus 1 squared. Negative 6 over 2 squared. Negative 6 over 4. That's negative 3 halves. Now plug in point slope form. Y minus the y coordinate equals the slope times x minus the x coordinate. And then we graph it and really hope that we didn't make any mistakes. So 6 divided by x minus 1, this is our function. And we said the tangent line should be y minus 3 equals negative 3 halves times x minus 3. We're hoping it's tangent right here. And yeah, if we zoom in, good. It looks like, didn't look like it super cleanly at first, but it kind of does here. And you could see it. Oh, my y-axis, you can't see it because it's covered by my camera, but it's because my y-axis is still like really, really stretched from before. This is what it actually looks like right here. So this looks a lot more like a tangent line, right? Very good, very good. And it's tangent at this point. Cool, let's do one more, 149. Oh, everyone's favorite, physics. According to Newton's law of universal gravitation, the force F between two bodies of constant mass, m1 and m2, is given by that formula. Where it's just the gravitational constant, 9.8 meters per second, or 32 feet per second squared, feet per second squared, meters per second squared. D is the distance between the bodies, and m are their constant masses. So part A, well, let's just write it down again. F equals G times m1 times m2 over d squared. Why does my G look like a 6? Oh, now it even looks more like a 6. All right, suppose that G, m1, and m2 are all constants. We're assuming that these three things are constants. Find the rate of change of force with respect to distance. So if this is a function of distance d, it wants us to find the derivative of this function with respect to d. This is a little unfortunate because this is a side comment. Normally when we take the derivative, we write it as d dx. The derivative with respect to x. If we wanted to take the derivative with respect to some other variable, we'd write it d, like this would be the derivative with respect to time. Well, if we want to find the derivative with respect to distance, we'd write d over dd, which is, it's just, that doesn't look nice. We'll write f prime of d. All right. how do we find the derivative of this? Well, we're assuming that this top is just a bunch of constants. These are just a number. We could use the quotient rule, or remember back to the first video, we could also use the power rule. These are just numbers. We could rewrite this function like this way, and then use the power rule and the constant multiple rule. So that the constants just factor out, and all we have to do is take the derivative. We can write this with a prime if we wanted to, the derivative of this, or you could write d over dd, which would be pronounced ddd. But we can use the power rule here, no problem. This is g times m1 times m2 times, bring the power down, and subtract 1 from the power. And then we can clean this up a little bit. It's negative 2 g m1 m2 all over d cubed. That is our derivative function. That is how the force is changing with respect to the distance between these two objects. As the rate of change of the force with respect to the distance between the objects. Part B asks us to find the rate of change of force F with gravitational, oh wait. Sorry, the gravitational constant was not what I was thinking of earlier here. I fail my physics for the day. Gravitational constant of that G, which is not 9.8 meters per second squared, on two bodies 10 meters apart, each with a mass of 1,000 kilograms. They're big things. All right, so find the rate of change of force. We already found the rate of change of force. Now it's just asking us to plug in and evaluate. All right, so we're just going to use this over here and say we want this derivative when they are 10 meters apart. Make sure our units are all on the right. Our units are all right. Our constant has Newton meters. Good. Because the distance is also in meters. They have to have the same units. The mass is in kilograms, and our constant has kilograms. Good. If this were given in like grams, we'd have to convert it. Otherwise, we'd have kilograms and grams. But ours are all consistent, which is good. So negative 2 times g. Oh no, I did the thing where I freaked out the book. G is 6.67 times 10 to the negative 1, 11. And again, the units for G are Newton meters per kilogram squared, I think. Newton meters squared per kilogram squared. And the mass are both 1,000 kilograms. So M is 1,000 kilograms, and M2 is also 1,000 kilograms. The distance between them is 10 meters. We're cubing that. And just to kind of keep a running tally, right? This is G times a mass in kilograms times another mass in kilograms divided by the distance cubed. So this is the units that our answer needs to have. So the kilograms, right, are going to cancel. And then 2 of these meters are going to cancel. So our answer should be in newtons. Wait. Yeah. Our answer should be in newtons per meter. Force is in newtons. Force is in newtons, and we're curious about the rate of change of force with respect to distance. The force is in newtons. How does that change with distance? Newtons per meter. With every, well, let's plug in our answer into the calculator and then explain this some more. So if we use Desmos for this, we're going to get negative 2 times 6.67 times 10 raised to the negative 11th times 1,000 times 1,000 divided by 10 cubed, right? All right, that's negative 1.334 times 10 to the negative 7th. Newtons per meter. There's two ways of getting to the units here. The first way is to just write what are all the units of these. The second way is to say, okay, force is in newtons, and we're looking at a derivative, so it's going to be newtons per unit of distance, newtons per meter. All right, and this says that if we have these two objects apart with this gravitational constant, and each mass being 1,000 kilograms, then as these things are moving apart, the force, the gravitational force between them, because there's gravity not just between us and the Earth, there's gravity between any two objects, then that force, the gravitational force between them as the objects are getting further apart, increases by about that many newtons with every meter that they move further. Sorry, decreases, right? It's negative. The rate of change is negative. So as these two objects are getting further apart, with every meter they get further apart, the force, the gravitational force between them goes down by about negative 1.3 times 10 to the negative 7th newtons. All right, and yes, you know, 1,000 kilogram objects that are 10 meters apart are not going to have a very high gravitational force between them. The bigger the mass, the smaller the distance, the bigger the gravitational force. That's pretty much it. Still got a nice little physics problem. Let me know if you have any questions, and have a good one.